Well, good morning. My name is Gary Richmond. I work for SaltStack, and I'm part of the professional services team. Thanks very much for coming to this session. This is on event-based orchestration with SaltStack. The reason I created this talk was when I first started with Salt a few years ago, I was looking at it through the lens of configuration management. And I was looking at it in comparison to other fine tools like Chef, Puppet, and Ansible. And it wasn't until I had been using Salt for quite a long time before I recognized that Salt is actually an orchestration engine first that happens to do configuration management really, really well. And part of what I do in the professional services team is I provide trainings and do on-site consultations with different companies. And I recognize that sometimes it's not always clear, if you're looking at it through that lens as I did of configuration management, that you also have a very powerful orchestration engine that you're working with. So the goal of this talk is to show you how you would do end-to-end provisioning, leveraging Salt's orchestration capabilities in a way that would be easy for you to integrate Salt with other parts of your infrastructure. So I hope you enjoy it. So our objectives in this demonstration will be to configure Salt API, which is a module that's built into Salt called REST Cherry Pie, to accept calls, and those web-based calls would contain post data from some external system. We'll use curl in the examples, but this system could be anything in your environment, such as ServiceNow or Cherwell or a custom self-service portal that you've worked on, or something completely custom. And then you'll leverage that to pass data at runtime to the orchestration system through the API to provision infrastructure in a cloud environment. In this case, we'll be using Amazon. So when you use REST Cherry Pie and Salt, you're tying in directly to the event system. The event system has 3 client interfaces generally that you would work with. There's the local client, the runner client, and the wheel client. The local client would be what you invoke when you publish a command in Salt. For example, salt star test.ping. You're invoking the local client by publishing something to the message bus. The runner client is when you want to invoke modules directly on the Salt master. A common one would be the jobs runner, where you could do things like jobs.active or jobs.list_jobs. These are things that would run specifically on the master. Then there's also the wheel client, which is what you would use for key management through the event bus. You might have a provisioning tool that provisions infrastructure outside the context of Salt Cloud, but still want to tie into Salt to manage key acceptance. You could have an API call accept a key for you of a node that you've provisioned. Okay, well, in addition to REST Cherry Pie, SaltStack Enterprise has an enhanced API as well with all of the same kinds of capabilities, but then you're making calls through the Enterprise API service, which is backed by the role-based access security, which gets you a ton of functionality in terms of security and deciding who can do what across different targets in your infrastructure. So if this is of interest to you, there is a talk later today covering the new features and the short-term roadmap of SaltStack Enterprise that might be very interesting to you because they will discuss the Enterprise API and its features in that talk. So I hope that's helpful to know. But let's get back to REST Cherry Pie, which is built into the open version of Salt. To install it, it's as easy as yum install Salt API. This example is Red Hat centric, by the way, so apologies if that's not your distro of choice. And this machine that I have configured here is running Salt, and Salt API is installed but completely unconfigured. So other than a fresh install of Salt and a configuration for Salt Cloud, the instance on the right has not yet been touched. So this is a very live demo, and anything could happen. Let's see how it goes. So the first thing we need to do after installing Salt API is establish a user that we'll use to authenticate Salt API commands. We're just going to tie into regular old PAM and make this happen. Okay, I was able to type that. And we'll also set up a self-signed certificate that Salt API will use. And in a moment, we'll configure Salt API to use this self-signed certificate that we just created with Salt. A couple of notes here. The password I used for this was Salt API, and that's not a very strong password. In your environment, please use a strong password for access to the API because this is a pipeline right into your Salt master. And then also, please use a trusted certificate so that your interfaces that you work with programmatically will trust what comes back to them, and then you won't have to be looking at log files on the calling interface to figure out what's going on. So I hope that helps save some troubleshooting. Let's configure the Salt master to use external authentication. We will tell Salt to use external authentication. In this case, it would be PAM. It could be something like LDAP. And we will tell the external authentication system that the Salt API user that we just created and will be validated by PAM has access to all of the runner modules and all of the wheel modules and all of the remote execution functions that you could publish. In terms of permissions, this is wide open. In your environment, you will probably have different user accounts with different levels of permission. Next, let's configure Raspberry Pi itself. Okay. We're telling Salt to run Raspberry Pi on port 8000 and to use the certificate and key that we just provisioned. With that, let's restart the Salt master and the Salt API service to use our updated configuration. That is all there is to setting up the Salt API. You'll spend more time thinking about security than actually doing the work. But let's see if it works. We'll use curl in this case, and we will issue a curl command against localhost on port 8000, and we'll hit the login endpoint. And with that, we'll tell it that we want YAML back and that we will authenticate with this username and password using PAM as external authentication, and we'll save the session that comes back in a cookie file. Okay, something came back. Let's take a look at this. We have return data, and the return data is telling us you've authenticated using PAM. You'll expire at this time. Here are your permissions. Here's the start time of your token. This is your token, and you logged in as the Salt API user. And I mentioned that we were going to store the session information in a cookie. Let's see what that cookie looks like. Okay, just a rather simple cookie with some session information. Let's see if we can run an execution module on this target. Okay, what happened? I targeted localhost on port 8000. I'm leveraging my cookie. I want YAML back. I'm hitting the local client. Remember local runner and wheel? The local client accepts targets. I'll target star in this case. And on this machine, the minion is the only minion here running on the master. And the function that we'll invoke is test.version. The return data that we got gives us this minion ID that's highlighted, and the version is 2017-7.2. This would be exactly like providing the command salt** test.version. We've just done it through the API. That's really the only difference here. You have access to all the same interfaces in the API that you do at the command line. Let's go a little bit further because something as simple as salt** test.version is pretty simple for our use cases that we'll probably come up with later on. In this case, we'll tweak the example by providing a command line argument to a function that requires one. So we'll look at grains.item and request OS. The only difference in the command is that we've provided arg as yet another post variable, and in this case, our OS is Red Hat. And this is identical to providing the command salt* grains.item OS. Now, getting YAML back at the command line is kind of interesting, but probably a little rough for a calling interface. So when you write something or leverage an existing tool, it's going to query Salt API and get something useful back. JSON is probably a much easier choice for you to parse and use in your environment. So let's see how to do that. And all we're really doing is changing the header. And we see now that what came back was not YAML, but a JSON string. And you can parse that and use that in any way you need to. And this would be identical to running salt star grains.item os -- out JSON. So now that we have Salt API configured and we've validated that it works by running a few simple test commands, let's move on and talk about orchestration states. Orchestration states, if you haven't used them, are states that run on the master itself. They run via the orchestration runner. And remember that runner means we're running on the master. And orchestration states are fantastic tools for providing a central point of coordination across your infrastructure. With Salt commands, you can use configuration management states on nodes to configure them. But what happens when you need to configure things across the infrastructure using intelligence that happens as you gather data from different parts of that infrastructure? You could use orchestration states to initiate states on different types of machines in a particular order. A common use case would be something like setting up a LAMP stack, where you have a set of Apache servers and a set of application servers and a set of MySQL servers and a set of load balancers. You could use orchestration states to provision in the order that you need your database servers, and then application servers, and then web servers, and then load balancers. And then as the web servers come online, they could add their IPs to the load balancer configuration, and all of that could be easily automated through orchestration states. So I hope that helps to set the context there. So let's do a really simple orchestration state. The next part of our example after this orchestration state will be setting up a webhook from Salt API through the event bus to our orchestration state. And for that reason, I will call this hook test. So let's create a directory for my orchestration state to live in. And we will create our hooktest.sls orchestration state. Oh, did I hit 2 files? Oh, thank you. I VI'd my VI. Let's fix that. Appreciate it, guys. Okay. Okay, we have an ID called hooktest_log, and in our orchestration state, we're calling command.run right on the master. And that's a point I wanted to make about orchestration states. When you look in our documentation of orchestration states, you will see that there are different interfaces for invoking orchestration states so that you can easily do things like targeting different nodes for your orchestration states. And sometimes it's not as obvious as it could be that you can just call regular old state modules in your orchestration states and just know that they're running on the master. It's a fantastic way to gather intelligence on the master itself as you coordinate your orchestration states. So hopefully that knowledge will save you some troubleshooting. So in this case, hooktest_log will just execute command.run, which is going to take the output of date and append it to our log file. To execute this orchestration state, we'll say salt-run state.org/org.hooktest. So it ran and it told us some interesting things. It looks like it succeeded, but let's be sure it succeeded by actually looking at the condition of the file. And sure enough, the date has been echoed into our hooktest log. So that's good. We have a running orchestration state. Let's do something a little more interesting with it. Let's have a way of triggering our orchestration state when an API event hits the event bus. So let's create a place for our reactor states because we're going to leverage the reactor system to do this. And let's create a hook test reactor state to go along with our hook test orchestration state. Okay, so we have a reactor state, but now we need to tell the Salt master that we want to react when a certain tag hits the message bus. I did it again, didn't I? Okay, so we have a reactor configuration. And what this reactor configuration is doing is it's watching the event bus for the tag salt/net-api/hook/hook test. When it sees that event, the reactor system will trigger the reactor state that we just created at /serve/reactor/hooktest.sls, which in turn will invoke the orchestration state, which will add an entry to our log file. Let's also make an update to our Raspberry Pi configuration. In this case, we are going to add an option to disable authentication on the webhook. Remember that Salt API user that we created? Well, sometimes you will be working with an interface where you don't get to control all the authentication parameters that you're going to pass through to Salt API. Usually the one that gets you is having to specify the external auth. And so what you can do is disable authentication on the webhook endpoint, which was in that ID we saw, Salt Net API hook. So anything that would go through there, with this enabled as true, you are bypassing security at that level. That sounds like a dangerous thing. It is. Be very thoughtful about when you're going to do that kind of thing, and be sure that the events that it will invoke are safe events for the people that you've allowed to invoke it. When you need to ensure that you know who the calling interface really is, what you could do is provide some sort of API key that you were to create and pass that through as post data to the webhook. And then when you go through the event system and trigger your orchestration state, use the Salt Master to determine if you have pillar data that confirms that this is a matching API key to something that you trust. If it does, allow it to proceed. Otherwise, don't carry out the action. I hope that makes sense. The other consideration I would mention when you're using Salt API is that you might choose to host the REST API interface behind a traditional web server like Nginx or Apache to give yourself finer-grained control over your web server configuration, who's allowed to connect to it, what ciphers are allowed, things of that nature. So with the reactor and API configurations updated, let's restart the Salt Master and Salt API, and let's determine if we can execute our hook test by calling that endpoint to trigger the reactor to trigger the orchestration state. And we see the word success, and we've catted our temp hook test log, and we now see a second date entry. So we know that our API call was able to trigger the reactor to trigger the orchestration state to update the log file. So it's kind of neat that we can do this, but it's not very neat if we can't make changes on the fly based on the input that we provide to our curl command, because we want the orchestration state to behave in a particular way when we provide different data for that run. Let's do that now by adding inline pillar data to our orchestration state. So we'll return to our orchestration hooktest.sls, and we'll add some Jinja to it. Imagine a use case where you might have a post-commit Git hook that you would like to have trigger Salt API to do something. Perhaps you want to commit code, and the post-commit Git hook would spin up new infrastructure, check out the latest version of your application according to the tag that you've given it, and run through a test suite. Well, that's a use case that you could easily do with just the amount that we've covered. In this case, we want to leverage a key called release that might correspond to a new code release for you. If we don't have release specified as inline pillar data, we could provide a default of latest. We'll then update our hook test log to leverage that value of release rather than simply using the date. So what will happen is we'll take the value assigned to the release Jinja variable and we'll echo that into our hook test log. We'll use salt.run and call state.org, org.hooktest, and we'll specify inline pillar data with a release value of 1.0. It looks like it executed successfully, but let's verify what's actually in that log file. Now we see 2 dates and v1.0. And in and of itself, that's not terribly exciting, but once you recognize that now you can provide runtime data through an API call and change the behavior of an orchestration state, the possibilities start opening up. Let's take the additional step of setting up a reactor that will allow web-based calls to be passed into this interface to activate the orchestration state with runtime data. So as we did before, we're going to add a little bit of Jinja. And in this case, we're going to use Jinja to get whatever data came through as post. And from our post dictionary, we will grab the release key and assign its value to a Jinja variable called release. And then this is the technique for adding these keyword arguments as inline pillar data through the message bus. So let's test our revised webhook. Well, the webhook ran. Let's see what's in the log file. Now we have version 1.1 as we specified for release post variable. So just to keep on track, we're passing post data through a web-based call to Salt's API. The post data is being captured with Jinja variables. The Jinja variables are being passed as inline pillar data to the orchestration state, which is now running in a specific way based on the data provided. So food for thought, how could you leverage this approach in your environment to automate activities such as provisioning, notification, or self-healing with Salt? Probably lots of ideas are already coming to mind. So a common use case that I work on in professional services with companies just like the ones that you work at would be creating orchestration states that accept inline pillar data from calling interfaces to provision infrastructure in a particular way, often through some sort of self-service portal for provisioning or other provisioning tools that you've integrated into your environment. So let's create an orchestration state that can gather this inline pillar data and create a node on the fly with the data that you provide at runtime. So this orchestration state we'll call create_vm.sls. Let's bring it all together. It's a little tough to read, isn't it? Let me grab this from a URL so that it's easier for you to see it. There we go. Much better. So what we have here is an orchestration state that has a sample invocation at the top, and this is in the presentation materials that you could download through the event app. What we'll do is call salt-run state.org, org.create_vm, and we'll pass inline pillar data through. And this pillar dictionary has a key of VM, the value of which is itself a dictionary containing hostname, role, operating system, provider, and availability zone. So we'll specify these things at runtime. The next step is to assign the public IP address of our Salt master so it can be leveraged in the Minions configuration. And in this case, what I'm doing is calling a Salt execution module, specifically http.query. And I'm specifying the URL to Amazon's internal metadata call to its public IP address, and I'm grabbing the body of that response and leveraging it as my assignment to Salt Master. The next step is to gather the pillar data that we provided inline, and we'll set that as a Ginger variable. And the next step is to provide a sane default for values which are optional. In my example, I've decided that role would be an optional value that you would not have to provide through the API. But then I'm going to say if the role is not in the VM, I will update my VM dictionary with a default role of Salt Minion. And the only reason I'm doing this is just to show the use case of providing a sane default. But my next options are a little bit more stringent. I want to provide a stateful check to confirm I've received all the data that I definitely need. So I will set an empty list called errors, and then I will look through my other variables and say, if I don't have host name or OS or provider or availability zone, then I will complain by appending something to my errors list. Once I've processed that, I will go through a pre-flight check to say, if my errors list has a length greater than 0, then something's wrong and I do not want to proceed. How do I handle that? Well, I'll use test.configurable test state to say that the result is false, and I will comment what the errors were, and I'll join them with the comma so that the person knows all of the steps that they missed without having to iteratively fix it. However, if all is well, I'll use test.succeed without changes and note that all parameters were accepted. If you skip to the end, you'll note a require requisite on this next state, and that require requisite says the pre-flight check needs to have succeeded if I am going to execute, because what it's going to execute would be a runner to launch an instance based on a cloud profile. One additional note on this example that's nice is if you want to run something in test mode in an orchestration state, even though you might say test equals true, that would just pass along to stateful calls, but executions would continue to happen. And a way of preventing them from actually executing if you're running in test equals true mode is to determine if the running ops test key has the value of true, then have some alternative action other than the thing that would be executing at this stage. Hope that's a helpful tip. But regarding our launching of a new instance based on a cloud profile, we see that we're going to provide a profile which is based on taking our provider and then putting an underscore and then our OS. And that would map to a provider listed in your Salt Cloud. That would map to a profile in your Salt Cloud profiles definitions. Next, we have instances. In this case, we're specifying our host name for the instance we want to create in this use case. And then we have something very, very cool, VM overrides. What you can do is specify a dictionary of values to override whatever you provided in your default profile. Let's save this state. And I also wanted to mention that if you haven't used Salt Cloud, the profile I'm referencing looks like this. It's really very straightforward. It's my provider underscore the OS and my default values, which can then be overridden with the VM overrides that we saw. Well, let's test executing this orchestration state and see what it does. We'll call salt-run state.org, org.create_VM, and then we'll pass in inline pillar data. And let's see if all of this worked. Oh, we have a slight pause here. We're starting to get information back from Amazon. At first, it'll say the public IP is not detected, but right now, Salt Cloud is simply querying Amazon, waiting for the instance to come up. Fairly soon, we'll see an IP address come in. For those who haven't worked with Salt Cloud, it's really a very, very cool addition to Salt. What Salt Cloud lets you do is specify one or more providers, and you could have one or more profiles based on those providers, from which you could use Salt to spin up infrastructure in a data-driven way, just like you're seeing here. Salt Cloud will reach out into your provider's API, tell it to launch infrastructure according to the parameters that you've specified, wait for that infrastructure to be available, and then connect to that new node and deliver the means to install Salt, as well as a pre-generated Salt key for that minion, so that when the Salt agent is bootstrapped onto that node, it comes up in a working state, already talking to the Salt master, just like we're seeing here. Right now, we're looking at the tail end of the installation of Salt 2017 7.2. So while this finishes up, let's proceed, and we'll tie this all together. In this past section, we've seen how to use a web-based call to trigger a reactor that passes post data as inline pillar data to an orchestration state, and then passes the VM overrides to the cloud runner, along with those additional parameters that were sent. And we provision a minion with the parameters that were specified at runtime. And now, if we run salt-key, what we'll find is that we have our Salt master as well as our fresh new minion 01. And let's make sure that we can talk to it. Ah, good. It's online and it's already in a working state. Let's see how to do that same call through an API call. So we'll update our reactor. Actually, in this case, we're creating a new reactor. We'll see how copy and paste from the PDF works in this case. We've got to fix that a little bit. Not too bad, though. Okay, I think we'll do okay here. So what we're doing is, just like before, we're grabbing our post data, and then from it, we'll extract our hostname, OS, provider, availability zone, and role. Now, one thing that's a little interesting, and I hope it saves you some troubleshooting, is role being passed through as post data is going to be a string, but we would really prefer that this be a list so that in our orchestration state, we can iterate through the available roles and have them be a proper list when we look at our grains data on the resulting minion. So what we'll do is use some Jinja to split the role from a comma separated list into an actual Jinja list, and we can even pipe that through something like sort so that they come out pretty on the other side. So with this much done, let's add another reactor configuration file that knows how to deal with our new create VM event. And we'll restart the Salt master to honor the new reactor configuration and any changes I made to API. And in another window, I'm watching the event bus, just so that we can see things happen. Because you might have noticed that when I execute a call through curl to the reactor system, I'm not seeing the response to that. It's issuing the command on the message bus, but there's nothing waiting like we get with the salt command. So we can watch these events happen on the event bus in real time. Let's make sure things are working. I'll just say test.ping. And we see things happen on the event bus. That is good. Let's do our test here and see if we can launch a brand new minion called minion 02 through an API call. I'm seeing things go by. Let's take a closer look. So on the event bus, we see saltnet API hook create _VM. And we see what was provided as post data in this call. Next, we see Salt trigger the orchestration state, passing that same post data, but this time it's as inline pillar data. Going forward, we see that the cloud profile runner has been invoked using the profile that we designated, as well as the VM overrides that we specified. Next, we see Salt Cloud doing its job by creating the minion, requesting about it, querying information about it, tagging it in the Amazon environment. Next, it's waiting for SSH. It's waiting for that node to come up to the point where you could log into it. And once that occurs, we see that it's deploying Salt on our behalf, leveraging the key files that were specified. Here you see the bootstrap script. We'll scroll through this because it's just a little bit long. Okay. And now we're seeing outputs so far. Right here I see Salt installed. That sounds like a pretty good thing. Let's check Salt key. We see that Minion02 has been created and pre-accepted. And now we've seen the Minion start event. So we can assume that this Minion is now online. Let's see if it is by publishing salt star test.version. Okay. So we have responses from our Salt master, of course, and Minion 1 that we provisioned earlier with salt-run. But now we see Minion02, which we provisioned through an API call to Salt. So with that, you've seen end-to-end provisioning from a web-based call through Salt's API, through the Reactor system, through the orchestration system, to provision a node with unique runtime values. And with that, I hope that gives you a great deal of flexibility in the things that you might want to do with orchestration in your environment, particularly when it comes to integrating with other tools that you've already established. For those who were to download this guide from the website for the conference, you might take a look at the next steps. I have an extra credit problem for you. My challenge is that you would create a simple state to install and configure Apache, create a top file in your state system that targets minions according to their role. And then for any node with the role Apache, then you would invoke the Apache state. Finally, you would set up a webhook to initiate the high state on the minion start event. And then lastly, issue one more curl command to launch another piece of infrastructure with the role Apache and confirm that when it's all done provisioning, it's already functioning as an Apache server without you having to have done anything beyond just the initial curl command. So with that, thank you very much for attending. Enjoy your time at SaltConf. And are there any questions? Sir?
Is there a way to get around restarting the master every time you add a reactor?
That's a great question. At present, there is not. You would need to specify a new reactor and then restart the Salt master so that the knowledge for looking for that tag is a part of the running process. There are interesting workarounds that you can come up with if you think you'll be doing a lot of these things. You could do something like create a reactor with a tag up to a certain point that would cause it to fire and just use star, and then inside your reactor state, inspect the rest of the tag to issue a particular reactor state. Something else you could do is sort of create placeholder reactors that are more flexible so you can make changes on the fly while you're testing. And of course, when you're testing reactors, please always do that in a development environment because you do not want to have an accident with a reactor in your production environment. Lastly, there is a concept of dynamic reactors that gets involved in the Python source code, and you would need a core engineer to talk about that. I hope that helps. Sir?
So you said the materials were available in the app, but it's not there.
Oh, that's interesting. Let's take a look at what I have on the website. And this should reflect what is in the app as well. But right here we see saltedo.pdf, which is the exact document you saw me copying and pasting from. Oh, the question was, where could you find the presentation materials that you just saw? And if you look at the conference website, under Event-Driven Orchestration for the Modern Data Center, you should find a PDF called SaltEDO. Sir?
Yeah, I guess questions. It looks like there's a URL you access. The ending part is get into the event tag.
Yes, that's exactly right.
How do we secure that such that we don't allow people to deny out and issue all this kind of thing?
So the two methods that you would use,
The user ID can use the LDAP to authenticate, but the user, trusted user, but I want to put it eliminate people from sending contact.
so the question boils down to how do you protect the Salt API from someone doing something they shouldn't? The two answers are what we covered in the beginning, where we specified what permissions the Salt API user would have according to the external auth configuration. And the second would be the part that I mentioned, put Raspberry Pi behind a traditional web server like Apache or Nginx, and leverage the permissions at that level that certain IPs are allowed to connect to certain URLs, as well as firewall rules that would say only certain devices are allowed to connect. And then the last piece of that puzzle is I showed you how to disable webhook authentication, and my suggestion then was to leverage an API key, pass it through the Reactor system, and during the orchestration process, inspect it with known pillar data, which you could access from the Salt master to validate that the origin of this call is a trusted source because they have the right key.
But so far, you only talk about where they allow to come in, but what they allowed to do after they come in.
So the other question here is, how do you control what someone is allowed to do through the Reactor? And that's the good news, because the answer is really rather straightforward. The Reactor state that you allow it to talk to is what decides what can be done next. And then you would pass that information to the orchestration state. Again, that is where you determine what can be done next. But let's take it one step further, because I think the part that may not be clear is you could send any string of text you want through the Reactor system, but if there's no Reactor state that's being listened for, nothing's going to happen.
But it's like this, if the same thing you can using like your case, using salt call, using API, using client local, and then using event or fire.
Mhm.
Those way you have a better chance to eliminate what they allow, what is not allowed. But using this address URL, they just directly attach this string to the event tag. So event tag bypassing, kind of you bypass this so-called event file. You just go directly taking that from that API.
So one last bit on the question there about how can we secure what this interface can do. The places to spend your time scrutinizing your own configuration is determining what permissions the user has, know what IP addresses can connect to your environment, be very careful about the tags that you honor and what Reactor states they trigger, and then please spend a great deal of time looking through the Salt API. The information that is on the Net API website, which is in the further reading here, will be very valuable to you as you decide how to secure your environment. And an exhaustive conversation on securing this interface is beyond the scope of this presentation, which is why I opted to disable webhook authorization. However, you don't have to use webhook authorization. You can specify on a case-by-case basis what user can issue what function. And feel free to come up after the talk if you have further questions about that. At the moment, are there any other questions? In that case, thank you very much for attending. Enjoy the rest of SaltConf, and good luck.